No.
Excuse me. So we have to run locally in notebook?
Yes.
Oh no, we cannot do it because the computer cannot install.
The computer cannot install.
Yeah, we don't have they took away administrative privilege from.
Well, you should not need those to install. You don't need admin permissions to install these tools typically.
Oh, okay.
If
So
you if you download the
maybe I try.
MiniForge, I don't think you need it, but because you can install local.
Yes. This is new to me. They just took it away maybe a couple of weeks. I downloaded this one, so just need a unlimited. Is this one? This one. From GitHub, I download.
Yes, but can you go to the website? There's some additional instructions on the GitHub page.
This?
So if you need to install Python.
Yes. I'm not sure. ARM, I know cannot install packages. But it's music. They just take this.
So wait. You need to follow the instructions.
Oh, okay. I don't need to open
So you downloaded Honda. That's great. You can go past that. It's fine. So you can only do this. So you downloaded the zip, right? Because you showed me before the right database.
Yes.
Now we need to set up the environment.
Well, this one?
You don't need to do that. You already have your folder which you showed me.
Yes, but I changed the name.
But that's fine. That's not a problem. You should continue from set up your environment. So we need to go to the folder. We need to go to the folder.
Let's see.
Uppercase dollar. Yes. Then you need to go inside the folder.
I'm not on zip. I just downloaded.
Oh, do you want to? Now you can call Conda if you want. You need to copy it. You can copy this one in the tree for it.
This one?
I don't think we raised it.
Oh, yeah, we know.
It takes a bit more work than setting up online, but then you're free to choose whenever.
Okay, thank you.
Do you need help as well?
I think so.
I need help because somehow
Oh.
I created an account, but the problem is
Oh, you're in the.
I
getting the local environment set up. We're not doing cloud or code spaces or anything like that. Okay, so it looks like you're missing. Did you use the YAML file that we provided? Or did you install using zip? Oh, individually. So what you're missing, so like the instructions say you don't have a Zuki backend, you don't have the visual rendering backend. So you need to install, I would recommend PyQt, PyQt 5. So to install some pip,
My friend, I'm not sure.
that's what you.
We're downloading the tutorial now.
No, yeah.
So CD.
So you only need one, right? You don't want to have more than one Qt backend because that'll also trigger the error. So if you use a fresh environment for this, or if you use an environment that has pre-existing things in it. Because sometimes what happens is that you have some other application that has Qt bindings and then they're not the ones that we expect, then there could be some problems. Right, but that's not using Qt, so the problem. So what if you go to your command prompt and you type napari? Will it run or will it crash? Oh, there it is. So it looks like maybe you're good. Yeah, right. Okay, so it has Qt here. No, this is not on Jupyter. So Jupyter should, when you run it in Jupyter, command, it should open that part of it.
So now that we have this file, environment, YAML. Oh, your code is really bad.
Just checking and I remember those results. I don't think I have.
Okay, cool. Yeah, so it must have been something with the Qt binding.
Are you two together?
No, unfortunately, it's an issue.
We can share together.
I started PyQt and there's version 5 and version 6, and they're all not mutually compatible. And so
Let me see the results.
that's why we don't actually bundle it anymore, because we kind of hope that if you install the previous
Once it's done, we run that chest environment.
sometimes you get
And then we can start the
Anybody else that
tutorial.
needs any help with getting Conda, a local environment?
Because you have your Conda is broken. I think if you can follow it from and then you can check your sheets down.
Hello everyone, I'll do a quick introduction. We are giving a joint tutorial on image processing right now. The first part will be, we will start kind of basic, go with the foundation, explain how you can view images in the space of Python and programming. Then we will go more into the depth of image analysis and follow up with filters and try to build an understanding for how image filtering actually works. And following that, we will go into segmentation, dividing images into meaningful regions, and also at the same time introducing Napari, an image viewer that's very useful in that realm. And yeah, we'll see how far and how quick we progress along. There might be some bonus stuff at the end, but yeah. We will also have several exercises in between. We try to give your people enough time. We will try to judge maybe if you're ready. It would be good if you're just ready and maybe just give a quick sign with a thumbs up or something, so we get a feel for how the room progressed, and then try to solve the solutions in front of you as well. If we are too slow or too fast, just feel totally fine to give feedback. Also, someone walking around, you don't have to, if you don't feel comfortable, just tell someone, and we will slow down or quicken up if that's a problem. Yeah, just a quick introduction. This is Stefan, this is Jordan, Then we also have Peter at the back and Eric helping you. Feel free to approach any of them, and yeah, hopefully we'll have a what to say, we learn something today.
We also have Slack channel.
Oh yeah, oh sorry, I forgot. And we also have a Slack channel, so it's totally fine to ask questions there as well.
Hi everyone, it's great to have you here today. I look forward to this tutorial. What we expect right now is that you have an environment in which you've got Python installed, you've got the prerequisite libraries installed, you can fire up a notebook, and you can load the course material. If you're not at that point yet, please indicate with your hand so we can help out. So this is roughly where I want you to be right now. Be able to open the first notebook on images as NumPy arrays. And what's that? Yeah, I can show that. Yeah. So when you're in the file browser and you see the markdown file, you have to right-click on the file and say, open with notebook. Otherwise, it's going to open it as a markdown file. And then you should be seeing something like this. All right. All right, so the first part of this tutorial is about how images are represented for use by scikit-image. Who here have used NumPy before? OK, great. So you probably already know everything that you need to know from this section. But NumPy arrays are the standard exchange format of array data in the whole ecosystem. So almost all the libraries accept NumPy arrays as an input. And we're just going to see what flavors of NumPy arrays represent images. So how do images look when they're represented as NumPy arrays? We are going to start by importing two libraries, NumPy, which we're going to give the short name NP. Can everyone see the font here? Must I make it bigger? It's OK? So we're going to import NumPy. We're going to give it the name NP. And we're going to import scikit-image, skimage. And we're going to give it the name ski. If you don't do those imports, then the rest of the examples won't run. You'll see that I'm running NumPy 1.26 and then scikit-image 0.24. These are all fairly new releases. NumPy actually just came out with a 2.0 release. So for the most part, it is compatible with NumPy 1. But there are a few gotchas when you add arrays and scalar values together and so on. But we're probably not going to hit any of those issues today. And for the most part, it's very trivial to port code from NumPy 1 to NumPy 2, so don't worry about that. But if you run into any issues and you have NumPy 2 installed, be happy to swing by and help you fix your code. NumPy 24 scikit-image 0.24 is the latest release, and that release supports both NumPy 1 and 2. All right, so let's get going. So when you want to represent data as an image, you're just going to be creating a standard NumPy array. And there are various kinds of images that you may want to create. You may want to create a gray level image. So a black and white photograph would be an example of that. You may have color images. You may have images with transparency. You may have volumes, like you would get from a microscope. Or you might have an image with some transparency in it. Like if you have a signature on a piece of paper and you want to hide the background, you'll have a transparency layer to that as well. But let's start with the very simplest image here. So we're just going to create a random matrix of values between 0 and 1. The array is going to have 500 rows and 400 columns. And it's going to be a floating point array. So yeah, values varying between 0 and 1. And we can ask matplotlib to show us that image, and there it is. So just a matrix, random values, 0 to 1. That's the simplest image you'll ever work with. Scikit-image also has a whole gallery of images that you can use to test your work on as benchmark images. Those are all in the data submodule. So here we're going to load one of those images called coins. So if you do ski.data.coins, that image is brought from disk. And we're going to print out the type of that coins variable. We're going to look at the data type and the shape. So that already tells us what the type is going to be. That's going to be an array, a NumPy array, standard NumPy array, and it's going to have a certain data type and shape. Sure enough, there's the coins image. You can see it is a NumPy array. Its data type is unsigned integer 8. What does that mean? What is the range of uint 8? Unsigned integers that occupy 8 bits or 1 byte in memory. What values do they cover? 0 is the lowest value because it's unsigned, so it doesn't have positive and negative. Okay, and we have 8 bits that can be either all zeros, all ones, or something in between. So if all those bits are set to 1, which value do we get? I heard it at the back. 255, there we go. Yeah, so these are integer images. They have values like 0, 1, 2, 3, 4, 5, 6, all the way up to 255. And in this case, the shape of the matrix is 303 rows, 384 columns. So lots of image processing libraries use X, Y, Z, etc. axes to represent images. But because we work with NumPy arrays, we use the same nomenclature there. So we talk about rows and columns, and if we go further, it might be rows and columns and planes. So how do you represent a color image? We've now seen how you do a gray level image. How do you do a color image? Well, a color image is a matrix of shape M, the number of rows, N, the number of columns, but you need 3 of them because you need to represent red, green, and blue together. You get other color spaces too, like hue, saturation, and value, but by default, we work with red, green, and blue. So here's an example of a photo of a cat. So let's look at the shape of that image. All right, so there's Chelsea, and you can see that the shape of that array is 300. So 300 columns, 300 rows, 451 columns, and 3 different planes, red, green, and blue. And this is also an integer image, so the values run from 0 to 255. Well, this image doesn't have a value above 231, actually. So since these are just NumPy arrays, we can manipulate those arrays, which will change the values in memory. And when we then redisplay the array, we should see those changes taking place. So I'm just using standard NumPy syntax here to slice into the image. And I'm saying take the rows from 10 to 110. So that's it's a section of 100 rows. And then the columns from 10 to 110. And where they intersect, you get a little block. The block is about 100 by 100, and we assign a value to that block. We assign the value 25500. So remember that we have this 3-dimensional array. So we have rows, columns, and then red, green, and blue. So when I assign this value, I assign 255 to red, 0 to green, and 0 to blue. So what's going to happen? We're going to draw on the image now, and what are we going to draw? What do you think? A red square, exactly, yeah. So, yep, there it is. So as I mentioned, you can also have a 4th dimension that would introduce transparency. We're not going to deal with that today. And here are basically all the different types of images we work with. So a 2D grayscale image, just rows and columns of different values. A multi-channel image, so rows and columns, and then your red, green, and blue. A 3D grayscale image, so that's where you have a volume coming from your microscope, for example. We have planes, rows, and columns. Or you can have a 3D multi-channel image. So you have planes, rows, columns, and then you may be scanning different stains. So those stains would be the different channels. Okay, so now we're going to do a very quick primer on matplotlib. Are you all familiar with matplotlib? You all used it before? Okay, so this is going to be a very, very quick refresher on displaying images with matplotlib, and everything you need to know for this tutorial, I think, is in this cell. Okay, so this is how you typically import matplotlib. We import it as PLT. This is the most common call for creating a new plot. So you say, give us subplots. If you ask for a subplot of 1 by 1, that's just a single plot. In this case, we ask for a subplot of 1 by 2. So that's 2 images displayed next to one another. What do you get back? You get the figure. And there's a lot of things you can do with the figure, like set its title and so forth. And you get the 2 axes. So the 2 spaces that you can draw on, you get those back. Axis 0 and axis 1. Then on axis 0, we display an image. And on axis 0, we set a title for that image, in this case, cat. And we switch off the tick marks. So by default, it shows you the different rows and columns. We switch that off. Image 1, we display an image of a rocket. We set the title. We don't switch off the axis label, so you can compare the difference. And we set the X label, the label that appears underneath the image. Then we plot 2 vertical lines on the image, and we plot just a jaggedy line at the following coordinates. And you can see that for the lines, you can set the color, you can set the line style, and so forth. And then finally, we just ask matplotlib to give us a legend for the 2 lines that we drew. Load the image, do the plot. Okay, there we go. Title, X label, tick marks, no tick marks, image on both sides, vertical lines, and a jaggedy line. Okay, that's basically what you need to know about image display to get through this. Any questions so far? Everything clear? Okay, awesome. All right, so NumPy arrays can have different data types. So we just spoke about the unsigned integer uint8. It's 8 bits or 1 byte long in memory. But you get much bigger integers in NumPy, and you get floating point characters. You get signed and unsigned D types. So arrays that either have only positive values or positive and negative values. And all of these can be used to represent images. You can also convert between the integer representation and the floating point representation. And typically, we work with floating point images internally. So here you can see I generate 2 images. The one is called linear 0. The one is called linear 1. The one is, in the first image, I have floating point values that start at the corner of the image and then increase. And in the second image, I have the same, but I've converted it to integer values. And you can see that those images display more or less equivalently. But yeah, they seldom, I mean, you can save a little bit of memory by using integer representation, but mostly internal to scikit-image, we use floating point to represent those images. And this is perhaps something to note is that in some places in the library, we still make the assumption that images will have the range, the data range 0 to 1, so that 0 will be black essentially and 1 will be the white value. We're trying to do that less and less because people are nowadays working, with a variety of data sources. So you may want to represent altitude above sea level, or you may want to work with temperature or rainfall. So it doesn't always make sense to have your image in the range 0 to 1. But that's sort of if you don't really know what range to use 0 to 1. If there's a specific reason to use another range, just use what makes most sense. And most of the algorithms in scikit-image don't care. Okay, but of course, so far we've seen images that we generated using the NumPy random module, and we've loaded some images from the example data set. But in real life, you're going to be wanting to load your images from your hard drive, and you'll have JPEGs and TIFFs and PNGs lying around, and you want to load those up. So what do you use for that? Well, the best library to use is probably image.io. pip install image.io, conda install image.io, and they support a very wide variety of image formats. Scikit-image has a wrapper around that you can get through the scikit-image.io module, and that just makes it easier to use image.io, but you can just as well use image.io directly. The library simply goes, reads the file from disk, and it gives you a NumPy array back that you can then use. All right, so you see here we do ski, so scikit-image, io, imread, give it a path to a data file, and then we're going to make sure we get an array out, and we're going to look at that array a little bit. And yep, there we get our array back. It's a uint8 array. It has a certain shape, and the values run from 0 to 255. Sometimes you want to load more than one image, so you may want to load an entire directory of images. So for that, we have an image collection. So image collection takes a wildcard as input, or wildcard separated by colons if you have multiple wildcards you want to specify. So in this case, I'm saying in the current directory, load all the PNGs. In the data directory, all the PNGs and all the JPEGs. Go. Okay, so it loads all those up, and it puts it in this image collection container. And the image collection basically just works like a list. So if you get the first element of that list, that's your first array. If you get the second element, it's the second array, and so forth. Okay, and then the details here, not super important. I just have a little example function that takes one of these image collections and plots out the different images in there. It's like handy to do a little gallery of all the images that you've loaded up. Okay. All right, so this brings us to our first exercise. And what I'd like you to try here is take an image and then draw the letter H on that image. So you're going to take the array that represents that image. You're going to make a copy of it, because if you modify it directly, you'll have modified the original image. So take the image, make a copy, and then manipulate that array until you see the letter H at a given coordinate. So here's how the function is going to look roughly. So take an image as input, take a coordinate, where should the H be positioned, and what should the color of the H be? There's a question? Yeah. Oh, that's it, yeah. If you finish with that one and you want to try a few more exercises, we've got 2 or 3 more. So the second exercise is about taking a color image and taking the red, the green, and the blue layers out and displaying them side by side so you can see what those look like. And then there's also an exercise about, where is that one? Oh, it's the second part of that problem, about taking 3 channels, a red, a green, and a blue channel, and combining them back into a color image and seeing what that looks like. And then the final exercise is about how to convert an image from color to grayscale. And you might learn something in that exercise about how the eye works and how we observe green very differently from blue. Okay, so give it a shot, and we'll check back in a few minutes. made it past problem 1? Okay, a few. Give you 1 more minute. All right, let's talk about the solution to problem 1. Well, first tell me, did you run into any difficulties? Like any issues that cropped up? It just worked first time? What? Okay, so there are 2 main approaches that I've seen. The first approach is where you take the input image and you slice out the first leg of the H, color that leg, do the second leg, and then the crossbar, and you assign colors to those parts of the arrays. There's sort of a sneaky trick you can do that makes for quite nice syntax. So instead of working with the original array, you slice out a smaller window out of the array, just the window that's going to contain the H. So once you slice that out, you get a view into the array, and you can assign into that view. So then you don't have to add the offset at every point, but you're still modifying the original array. So let's see what that code looks like. So here's the first version. So make a copy of the input image, grab the row and column that you want to put the H at, and then, like I said, every time you have to add row, right? Because that's the offset, or you have to add column because that's the offset. So there's 1 leg, 2 leg, 3 legs of the H, and yeah, you get something like that. These solutions are in the repo, by the way, so you can open them up and take a look. The file, I think the image file path is off by 1 ... Let me show you. Where's Chelsea loaded? Oh, this just uses Chelsea. But yeah, if you're loading balloon, it's going to give you an error. That dot just needs to be 2 dots, and it'll load fine. Okay, so the second solution, where's that H? Here we go. There's the second form of the solution. So you see, we slice out that little window in which we're going to draw the H. And when you do slicing in NumPy, depending on exactly how you slice, but a lot of the time you get a view onto the original array. So it's the same data. And then you can say, okay, now go and set the values for the different legs of the H inside of that window. And that should do the same thing. Yeah. Right. In the second example, we just take a color image and then we visualize the red, the green, and the blue channels. And you'll see it corresponds with your intuition. So looking at the bushes, not much blue in there. Looking at the ocean, not much red in there. The ocean has sort of a combination of green and blue. The second problem there was you got these red, green, and blue channels, and you were asked what happens when we combine these. So, well, in this corner we'll have red, so the white will become red. That's the green channel, so that will become green, and the last one will become blue. But where they overlap, you expect to see white. Yeah, so that's what you see when you combine those three. And then the last example, what I wanted you to note here was that when you take a color image and you convert it to gray level or to luminance, you don't actually take a third of the red channel, a third of the green channel, a third of the blue channel, and add them all together. Your eye doesn't work that way. We weigh green much more heavily. So you'll see the weight next to green is 0.7, whereas the red weight is only 0.2, and the blue weight is even less, 0.07 there. And that corresponds to the sensitivities of the sensors in your eyes. Okay, I think that's it. Yeah, any last questions about this section before we move on? Great.
Perfect, okay. So you made it through the first part, and now we will go a bit into more depth on actual image processing, rather than just manipulating arrays or images. And yeah, we will have a break within this section, so just you're aware. But for now, let's continue with this. So what is image filtering? Image filtering is a process where we enhance or subdue certain features inside an image. It's very commonly used as a pre-processing step to manipulate the image such that the following process, for example, a machine learning algorithm or something, is able to view more meaningful data in the image. It's also used to suppress noise or unwanted features. And it's a very generic term. So let's redefine it somewhat more. And by that I mean we'll start looking into local filtering. And like the name suggests, local filtering is all about looking at the immediate surrounding neighborhood of a single pixel, doing something with that, and then manipulating the pixel according to the filter. And for a start, we will go one step back from 2 dimensions to 1, because it's just way more intuitive and simpler to understand what's going on here. So in the beginning, we will just define a very simple step function. We start at 0, then have a jump up to 1. Very basic and common to understand, but a great way to demonstrate what a filter actually does. And to make it a little bit more difficult and I guess more realistic, we will add some noise, randomly generated, with a certain seed, so you all get the same noise. And what we can already see, recognizing the original shape of the function is way more difficult now. So this could be, I mean, you can just, with prior knowledge, you can guess that this might have been a step function, but who knows really how steep the slope here would be. And what we can do to recover the original, and let's say our goal is to recover the original signal, and what we could do here is let's start averaging. We know this noise is supposed to be somewhat randomly distributed, so adding 1 pixel to the one on the side, dividing by 2, should give somewhat more of a original or somewhat closer to the underlying truth. That's not noise. And if we do that, yeah, okay, it's gotten a little bit better, but it's still not great. We start to see something, oh, here could be a step here. So maybe let's do that for 3 neighboring pixels. So we take the first signal, or we take 1 pixel, we take the one in the center and to the right, and then we divide by 3, so we still get the same amplitude. And if we do that and overlay with the prior stuff we computed, we can see it gets better step by step. So you can imagine the more we do this, the more we will maybe recover an idea of the original image. Well, you might have noticed this is gotta be annoying if we want to average more than, for example, 3 pixels. Just imagine we want to do this for 50 pixels or even more dimensions. Doing all that by hand is kind of annoying. And what we can do instead is introduce a concept that's called convolution or averaging kernel. You don't have to understand those terms right now, but we will explain them step by step. And as a start, you can imagine the concept that we will take a window of the signal, a snapshot, and this window moves over the signal bit by bit, and at each point of this window, we will take what we're currently seeing. For example, in the case of a window that's 3 pixels long, we will see 3 pixels. We take those pixels, weight them to a certain, with a certain weight. In this case, for example, 1/3. I'll explain why in a bit. And then sum them together. And the weights in this case, we want to average it. That means we want, if we have, for example, if we have a window and we're currently seeing 1, 1, and 1 as pixel weights, in the end we want the average to be 1, so we need to divide by 3 if we sum them together. That's the reason. That's still basic averaging. The only difference is that we now specify how this window and the weights look beforehand. So we're not like taking a single pixel and summing them by hand. We actually define the window before, 1/3, 1/3, 1/3, and then we move it along the original signal. And the function that allows us to do this is this convolve function. So it does, first we define the mean kernel here. This is just what we have above here if we were to print that. And we say convolve this with original signal and the mode valid. I will get to that in a bit, what that is about. And then we plot it. And if you compare, this should look somewhat very similar to the green signal we already got. So great. Let's see this in action, maybe, interactively. This is not a great look. This is supposed to be interactive. If you're following along, maybe for some of you it's working. I don't know why it isn't working right now for me. Maybe it's something to do with a simple interface. That's great. I'd still love to demonstrate it. Maybe let me just restart the kernel.
0, 0.
Hmm?
Restart kernel 0, 0.
Oh, okay.
You have matplotlib inline and stuff?
Yeah, at the beginning.
First code still, yeah.
That needs to be pushed.
Why is it working for the other people then?
Maybe it's changed.
I don't know. Should I manipulate this first line?
That's a problem.
Shall I try to install this right now?
Yeah.
Yeah, okay. Okay, now you can see some live debugging going on. So if you are like, if it's working for you, you can already play around with it and maybe hopefully build some intuition how this works. Should have just installed pip. It was already installed. Apparently, maybe.
So did you install IPL?
Excuse me?
Did you install IPL?
Yeah. That's what I did right now. Okay. Fingers crossed. Ah, okay. Perfect. So we can now where is it? Step along a little. Okay, I don't know why it's reloading. I think with inline it's just maybe nice. Let me try that. Okay, now it works this way. I don't know. Okay, glad that it works. And what we can see is these 3 blue samples moving along. But what we also see is, you might have noticed this, and this will become relevant later. The first filtered signal, the orange one, only appears once we are 3 signals with the blue inside the signal. And this will become more apparent if we do this with more samples, but more on that later. Just know that this is happening right now. And as we move along, we kind of follow the signal, but with a certain smoothing effect. And yeah, we can also do this with 11, with a window length of 11. And if we do that, we get an even heavier smoothing. And demonstrating that, you can now really see this is 11 signals deep in, or the window has already moved 11 samples deep into the original signal before we get our first filtered value. And this is also visible what happens at the end. You see our filtered signal gets shorter, or at least it looks like that. And that's a quirk of the convolution, that we have to do something about the fact that the kernel only overlaps in certain parts with the original signal. So we have actually a state where the kernel starts overlapping, but there's something to the side, unknown signal. We don't know those values. And that also happens at the end of the signal. And there are certain ways to deal with this. And first, what we can do is we can say, okay, we want to, we use mode same. And what this mode is actually doing is it's taking the side of the signal, padding it with zeros, and then just convolving everything. And at the end, it's cutting off the sides again so that it's the same length. And because we are padding with the zeros, you can see you're starting to see edge effects. That's this orange filtered line going down. And why is it going down? Well, because we have zeros here, and the average window is moving into the part that's 0, and that's something to be aware of if you're using the mode same. You're introducing effects into your filtered signals that might not be something you want, or maybe you just don't care about it. It totally depends on your application. And we can also show this in action. Here we already see we are starting with 0 images, and if we're moving along, on this side it doesn't really matter that we are padding with zeros, because the signal or the noise original signal is around 0, but on this side we see that it's pulling the signal down. And now we're coming to the first exercise. So the goal here is to look up the documentation of the SciPy and image convolve function, because it has some nice features. Especially maybe look at the documentation of the mode parameter, and figure out if you can apply and use a keyword that may be able to do something about these edge effects. I might give you like, I don't know, 5 minutes, and then I will slowly solve the problem here, or just give a thumbs up if you're ready, so we get a feel. So I'll slowly start solving this now maybe, and you can move along if you haven't already solved it. So let's first take snippet from above, just copy it because it's quicker. So we can use different modes here, and I'm gonna use so these modes only really differ. For example, we could use reflect or mirror, and these kind of do what they say. If you look at the help or guide help here above, they only really differ in what they do with the edge value. So mirror doesn't include the edge value when mirroring. Reflect repeats it one time. We could also use constant nearest here. The problem with nearest is it's also sensitive to noise. So if you have a very big offset due to the noise at the end, that might impact the result somewhat more heavily. So it's better to use maybe mode reflect. And we're gonna name this reflect, and because we are convolving with the kernel 11, we just do that. We use same here, and we use reflect here. And we run it. Okay, and what we start to see now is this mode, this valid mode, suddenly drops. Or no, this is not valid. This is actually the same. Just make that right. Because we are padding with zeros, which are weighted into the kernel. And here we are reflecting, and we can nicely see that this doesn't impact our right edge so much. So with that done, maybe let's look at another type of filter. So up until now, we've only been averaging and taking the mean of our kernel, but we can do more stuff with our kernel. And for that, let's restart with our very simple signal again without the noise. And as an exercise, I want you to take a quick moment to think about what happens if we use this as our kernel. -1, 0, and 1. What might happen if we move along, weight each pixel of those three with these weights? So we take the leftmost pixel, multiply it by -1. We take the middle pixel, multiply it by 0, and the right pixel and multiply it by 1, and then we sum those together. What might happen if we move this along the step function? Someone, any ideas? And maybe is brave enough to tell? Excuse me? Yeah, it's kind of like acting like a derivative on the signal. And what will happen is, in this part, everything's 0. So there's nothing really to sum. It should still be 0 if we multiply it. In this area, everything cancels out. So we have -1 on the one side, we have 1 on the other side, we sum those together, 0, and the middle sample doesn't contribute anything. But around this area, we suddenly get something that should give us a signal. And if we run this and plot it, we get this. So now we're introducing a second, maybe, concept. Up until now, we've used convolved most of the time. And convolved has the convention that it flips the kernel around. Let's call it, for signal processing reason, for historic reasons, it's just a concept to be aware of. And then it's the same as the other concept, which is correlated in this function-wise. So correlated just takes a terminal and moves it along. Convolve flips it around and then does the same. So if you were to flip the kernel around manually beforehand, then you can use these interchangeably. But going on from now, just because it's maybe simpler to understand in this context without the flipping, we will use correlated for now. So yeah, and now let's look at another nice property of these filters. First we introduce noise again, and we can see that if we are trying to detect the change here, it's very difficult. So if this were a perfect world without noise, we should detect the original step in the middle, but we don't. And we kind of do, but it's not really obvious. So this could just be a fluke or some noise, and we can't really be sure. And these derivative filters can be very sensitive to noise. So what one can do is together with taking the derivative, also smooth the filter. And for this, we take the smooth signal we smoothed earlier. We take the derivative, and we can already see we get a nicer signal in the middle, which we can more easily identify as, oh, here's a big change happening right now. And the nice thing about this is we could apply this interchangeably. It doesn't really matter whether we apply the derivative first or the average or the mean filter. And this also means that we can combine the kernel and that we can combine both kernels beforehand and then just apply it at once. So how do we combine them? Well, we just correlate them with each other, which will start to look like this. So this is a combination of the derivative filter and the mean filter. It's also gotten wider because we actually want the full effect of the filter, so we used full here, and the overlap is, when it starts overlapping, it's actually then in the end five samples wide. And if we apply this, we get the original signal. If you are wondering why this seems like there's some offset between samples, that's just because we are switching back and forth between SciPy's and image correlate and NP convolve, which are treating this slightly the same. If we were to replace everything with NP correlate, then you would see that everything aligns here. Okay. Another very essential filter type is the Gaussian kernel, or the Gaussian filter. And let's first look, many of you might have encountered this already, but for completeness' sake, let's take a look for now, how it might look. And if we do a very low sampling, it somehow looks like this. So this is only, I think, 16 samples wide, so we still have some kind of edge here, but we can already convolve it with a difference kernel, and then we get this kind of wave-like function. And applying this to the original noise signal, we can see that maybe we can get even a better effect here. But for this example, it doesn't make that much of a difference. We will have an example where we can see why we may want to use Gaussian filters instead of just simple averaging instead. Because next we are going into images, maybe this is a good time to take a quick maybe 10-minute break for you guys to reset a bit, and then, yeah, we will be back in 10 minutes. have to set up according like we actually like decided to do this instead or whatever this is the thing and do pip install. I mean, you might just have to give them time for them to set it up and you're the judge how problematic it's been.
Okay. And I think it might already be there because we have not time. Okay. And,
It might be already at one.
is it busy? No, it does.
So I will slowly pick back up. Yeah, so right now we've only really dealt with one dimension, and now let's apply this knowledge we gained with 2 dimensions. So first let's create a very simple image. One of the simplest we can imagine is just a field of black with one square in the middle represented by ones. And if we plot that as a grayscale, yeah, we just get black for the background and white for the foreground. And applying a mean filter in 2 dimensions means we don't apply a window of 3 samples wide. We apply a square of 3 samples wide. In this case, we can create it again with full, and we divide by 9 this time, because if we sum everything together, it's 9 samples. We have to weigh and divide it by 9. And let's see what happens if we apply this to the bright square we just created. We can do this again with scipy's and image function again. And what happens is on the edges, because we have an overlap of 3, the background gets brighter a little bit, and the other values get darker because they're impacted by the background. And only the middle sample, where there's an overlap of where the kernel exactly matches our foreground, we still retain the value of 1. And we can also show this in action, and thankfully this works. So there's nothing really happening until this point, but here we start to overlap. So actually the sum of our kernel gets brighter until it gets darker again. Kind of see how it smoothed out our square in the middle. Just be aware, this is still a value of 1, even though it's not white anymore. That's just a quirk of the demonstration we've implemented. It's because it's overlaying this colored square here. It's just a matter of assigning colors to values. Yeah, and now let's apply this to on a real image. We take an image from scikit-image, which is just in our data module, and we to make effects more visible, we sample it down. We make it pixelated. We do this with by taking only every 10th sample from the original image, which will result in this. Just now, if you actually wanted to downsample an image at some point, don't do it like this. Use something like scimage, transform, rescale. That's the proper way to do it. But for now, we actually want this kind of pixelated, noisy image to demonstrate stuff. We also demonstrate a convenience function just to show all images we give it side by side. So just that's how it works. And let's apply the mean filter on our image. We just correlate it with our mean kernel we've defined earlier. And yeah, we can already see that it especially allows the noise. So these white samples in the middle, they kind of get canceled out. And it's smoothing the image somewhat. So nothing really unexpected there. And now we come back to the essential Gaussian filter again. And this is a good example where we can show why you might want to use a Gaussian filter instead of just a mean filter. First, let's apply it on the white square we originally had. So you can see it looks somewhat similar, but there's a difference in that the middle is also affected. And these ones, you can't really see it. It's very subtle, but this background is also brighter than in this case. And that's because the mean or the Gaussian filter is actually, like in theory, it's infinitively wide. It never gets to 0. It only approximates 0. But for in practice, we can consider it to approach 0 in 4 sigma from the center. And sigma is like a variable that defines how wide the Gaussian curve is. And we can Don't worry, we will show this in a bit, how this actually looks. But now let's apply this to the image. And again, looks very similar. It's just averaged and smoothed out. But what happens if we use a way bigger size to average the image? So we just use a bigger area to average the image. And here we start seeing a difference between mean and the Gaussian filter. So for the mean filter, you kind of start seeing these artifacts. And that's because the image is weighing, it doesn't matter how far the pixel is away from the pixel you're actually currently evaluating. So a pixel on the, far away in the corner, 10 samples away, is still weighted the same way as a pixel that's right next to your current one. So that's an advantage the Gaussian filter has. It weights pixels according to the Euclidean distance from the position you're currently at. And that is what leads to these artifacts for the mean filter, and the Gaussian filter is just way nicer about this effect. So you also see this part is way blacker instead of, I think, oh no, that might have just been perspective. And now let's build some intuition for how the Gaussian filter actually looks. So what we can do, we just define a single black image, and we put a single bright pixel in there as a spot, and then we convolve it with the Gaussian kernel of length 45. And the result will tell us how this bright spot is actually distributed over distance. And we in turn just get, again, this is how our actual kernel that this function applies actually looks. And as an exercise, I'd like you to create a profile of this cut through the kernel and plot it as a one-dimensional line and graph. I might give you maybe 5 minutes, and then I will show you how I do it. So who figured it out? Maybe a quick show of hands. Yeah, that looks like I could slowly start hacking away at it. So like Stefan already showed you earlier, we start with creating a figure and an axis. And this time we just don't give it anything because we just want a single axis. And we know that we want to plot something. And what we want to plot is we take the kernel. And we know we want to slice this kernel. And now we get to something that I myself are sometimes still confused. We know we want to take this slice. In this case, it doesn't really matter whether we take it horizontally or vertically, but sometimes it does. And it's very easy to confuse that in your head. And also matplotlib has its own convention on which axis is shown. So one way you can usually try to guess which dimension you actually want to operate on is, for example, manipulate it and just look at the result. So for example, I could slice, I could just shorten this dimension by, I don't know, 20 pixels and take the original dimension, and we see, okay, if we manipulate the first dimension, this is not the dimension we actually want because we want to manipulate this dimension. We just show it. If we make this 10 shorter, okay, we manipulate the dimension we actually want to slice. So I'll take the kernel, I'll take the entire slice from that dimension and use the middle. And what we get is a representation of the profile in the middle, and this is just the Gaussian function as you might know it, or the distribution. And you can see it starts to approach the 0 at the edges. Okay. Something that we've already touched on with the whole difference filter and taking the derivative in some way is basic edge filtering, and that's a very common thing you want to do, or you might want to do in image processing. You're interested in where the signal or the image actually has borders, where something happens, where something's changing from dark to bright, and the quicker and stronger the change is, the bigger or the border you might say is. And one way you can do this, you just apply our original difference filter as a kernel again. And if we do this on the actual image, the camera image we already had, you can see, because we are applying this vertically, I think this case from top to bottom, we can see we especially pick up corners that are facing the top, or are horizontal in this case, and if we were to do the other way around, horizontally, we would start to see borders that are vertical in the image. You can also see that, oh yeah, okay, this is just the shape of the kernel. And as an exercise here, I'd like you to do what we just did, but for the horizontal case. And once you've done that, because we might just be interested in where's stuff changing in general, there's a way to combine these two results into a single result, and the formula for this is we've written down here. This is how you combine the two results. Yeah, I mean, I think I might give you again 5 minutes and then slowly start solving the example. So how many of you worked it out? Maybe quick show of hands again. Mm-hmm. So again, I'll just copy what we did earlier and just modify it somewhat. And I'm lazy, so I'll just add the transpose here, which just flips it. Sorry?
That's cheating.
No, that's just being efficient. And then we'll plot the horizontal one, and as I said earlier, you can see that the direction of the edges changes somewhat. And if we want to combine that, we just take the formula we mentioned before, take the horizontal kernel squared plus the vertical one squared. You might recognize this formula from Euclidean distance calculation. And then we just plot it. Yeah, and we can see we get a way nicer representation and of the actual edges. So what we also notice here, before we still had the direction in the filters, so it mattered whether the edge was like if the signal was going down or going up, like if the value was deprecating or not. So where the signal wasn't like doing anything at all, it's just gray, which represents like no change at all in this case. And matplotlib dynamically adjusts the grayscale color map, meaning the darkest value is, for example, in this case, some minus value, and in this case, with bright values, it's I don't know, +1. And in this case, because we are squaring it, everything becomes positive and then just gets combined and squared. We just get the smallest values are 0, and we just get the result will just tell us, okay, there's a big change here, but it won't tell us anything about the direction or of this change. And for many appliances, this doesn't matter. For some, it might, and then you just have to account for what you might actually want. And there's also another essential filter that deals with this, that has some nicer properties to compare to what we just did. Because if you consider this just gets applied in one direction and then the other, and what happens if you have a border that's, for example, diagonal? You might still detect it, but the weighting is somewhat off, and there's just a nicer way to go about it. And you can look at the documentation and how this kernel looks differently. And this is for the vertical kernel, which is still there's a directional component. It's -1 and +1 on one side, but the pixel in the direction it's applied is weighted more heavily with a 2. And let's see how that looks applied to the square, and it should, in this diagonal case, it should just have some nicer properties of detecting that. And if we apply it to the original image, it's also somewhat, the border gets somewhat smoother, like more continuous compared to here, especially here where you have a lot of, you might say it's more jagged in the value-wise. And what we can also do, like we said before, you can often combine these edge detection filters or derivative filters with smoothing. And in this case, this has two consequences. First, our edge gets wider. This is something you might care about or you don't. You could still try to approximate the middle of this border, but it especially gets more useful in this area where there's a lot of noise currently in the unsmoothed case. And when we smooth it, we get some better reconstruction of the actual borders that are happening in this region here. Now, as a bonus, we want to go into something that's actually a funny or curious similarity between what you might have heard of as convolutional neural networks. And in the end, these kernels are just like a convolutional neural network you might have trained between a set of source data and target data you actually want. And we can just act like the output. If we apply the horizontal Sobel filter to our image, we receive this result, and we can just act like this is our training data. Well, we can just act like this is our what we actually want to get from the image, and this is our original input data. And then we are looking for a convolutional neural network that maps this image to this filter. And for this, we've put down a quick set of instructions you can follow along to solve this or to emulate this. I might give you maybe 5 to 10 minutes, depending on how long you want. You can also, like, if you don't get along, you can ask. And in the end, I will demonstrate how you might do this. And then we also almost at the edge of this part of the tutorial, and might take I think there was supposed to be some coffee break or something. Then maybe it's good timing. Okay. Yeah. Go hacking and ask questions if you have any. So, any people who want more time or have already figured it out? Who wants more time? Maybe show of hands. Okay, we can wait a bit. So I'll slowly start moving along each step here, and you can guys feel free to interrupt if you're unsure about something or something is still confusing you. So as a first step, we are there's a tip to use view as windows to get snapshots of this kind of window we just set. We want a window of 3 by 3 pixels of each part of this image, and this convenient function from scikit-image actually allows us to do this. And we start by import this image as sky, sky. We use the image, and then looking at this to make it perfectly clear, we say we want a window shape of 3 by 3, and then we print the shape of windowed. And we see, okay, we have the original image dimensions, almost, and 3 by 3 on the 2 new dimensions. And if you look at the shape of the original image, it's 512. So why is it 510 now? Well, that's because we want a 3 by 3 patch, and that means we have to drop the edge, because otherwise we would go into territory for which we don't have any values. And this is just how view as windows treats the borders of the image in this context. And once we have that, yeah, it's the same with the valid convolutions where you have some overlap or you don't. And as a next step, it tells us to use reshape to get a patch of 9 pixels. And what this means is we want one dimension that's n pixels long. So it's supposed to be 510 times 510, and the other dimension is supposed to be 9 pixels, just flattened, our kernel, and this is just 3 times 3. So we can easily do this. We just use window. And this will be also this will already then be our feature matrix. So let's call it X, to use a convention from machine learning. We take the windowed function, reshape, is 510 times 2 and 3 times 2, and then we again print the shape just to be sure what's going on. And we see now we have a nice feature vector that has 260,000 samples and then the window of 9. The next step, we also want to create our target vector in this case. And in this case, we can use Ravel quickly to get it. Target vector is usually named Y in this case. And we just say, okay, we have the target. And we just Ravel it. Oh, and what we need to do, we need to before we just Ravel it, because remember we only have 510 pixels, we also need to shrink our target vector in the same way, because we don't really use the border pixels as ground truth. So we drop 1 pixel on each side. This is how we do it, by slicing, and then we Ravel it. And again, just to see what's going on with the shape, we print it. And we can see, this nicely matches our feature vector. So Y gives us one desired value for each of the 9 values in the window. And at this point, scikit-learn comes into play. Linear model. Logistic regression. Create the model. With a liblinear solver, and then fit the model to the actual data. And the fit is then saved in these coefficients. And now if we print them, it takes some time, we see, okay, currently this is not really looking like our Sobel whites. Remember, we wanted, from earlier, where did we have it? We applied, I don't know, horizontal, vertical filter. I was scrolling too early. We wanted to get something like this, but we didn't yet. And the reason for that is we still need to scale it. So right now, this vector is has a different scale. But what we do now. First, before we do that, let's reshape it to something to the layout of our original kernel, which is 3 by 3. And then we know this sample and the edge should probably be 1 or -1. And the way we can scale that or recover the original signal we divide it by the sample that should be 1. Let's use this one. Okay. And then we get an approximation of our signal. So this already starting a lot more like we expect. It's still somewhat off because we can see while this is a small value, it's still not 0 like we would expect. but we can cheat a little bit and round it very heavily. For example, just to one digit, one significant digit. And this is starting to look a lot more like our original Sobel filter. So we can see that the logistic model just approximated the relationship, which was this horizontal Sobel filter from the data. That's just what a convolutional neural net is. It's just a mapping of input pixels to output pixels in that sense, if you put it simply. And as a final closing remark, there's as a final quick closing remark, there's also nonlinear filters. Right now we only had filters that are that don't manipulate the image in a very nonlinear way, but there's also, for example, filters that sort each pixel in the window and then, for example, take the median pixel. That's the median filter you might have heard already about. And a nice property of the median filter is that it preserves edges in a somewhat sharper way. And this gets even more apparent for if we don't look at the pixelated image, but for example at an image that's full scale. For example, this coin example, let's say we want to detect coins in this example. We don't really care about the face of the coins yet. So instead of doing the mean, we can say we are doing the median. And there you can see we have a very crisp edges still preserved. And can then work from there, for example, apply a Sobel filter to say, oh, okay, this is where the coin starts, that's where the coin ends. Yeah, if you're interested in further reading, there's, of course, our documentation. Okay, then let's take a break for now. Everyone grab a coffee, and we'll back here in, how long do you want? 10 minutes maybe again, and then we will start with the second napari themed part of the tutorial. Thank you.
Testing, testing. Oh. Magic here.
Maybe it's one more shot to ask if everyone's got their environment set up locally with napari,
Okay.
just in case. Because the notebooks, in principle, you could be doing them wherever, right? We haven't used anything visual.
Let me just change everything here. Is the environment working for everyone? Or does anyone have any issue? I think this is the time to try to fix it.
Maybe you just open a terminal and just type in napari and see if it works.
Okay, can you, does it work from here? If we do, probably,
Oh, shoot, that's smart. That should work.
oh,
Does it work? It does work. Oh,
Yeah.
okay, so maybe people can try that, just to make sure. Exclamation point napari in your notebook, and then hopefully you get something like that.
it's just a sanity check to see if the viewer is working.
Because napari requires some additional backends for the graphical part that Jupyter doesn't usually use, so exclamation point napari will double check that it runs, and then you can hit Control Q to close it. That's really, really clever. I have never thought of doing that. I'd always like go into the thing and launch a terminal in the Jupyter and then type napari in the terminal.
And you can even install packages like this, so you don't have to close Jupyter, install the
But you can
package.
use like %pip, right? I think it knows about that.
Oh, I usually use the exclamation mark, but that could work as well. Okay, let me.
Whoa, that was big.
Which?
Show of hands, is it big enough? Can you all see this %napari? If everyone could try to run this in a notebook, any notebook, doesn't matter, just to double check that you launch the GUI of the program.
Can you run this line? Does it work? Does
Thumbs
it
up
open?
if it works, I guess. Okay, there's a few people where it works.
Thumbs down if it doesn't work. Oh,
Okay.
it doesn't work.
All right. I'll take the first and then the back.
Can you check? Okay.
I'm sorry, what? Yeah, we haven't figured out why that locally is supposed to be broken, but if you, it may take a moment, if it's the first time, it may take a little while, especially if you have any corporate security software on your laptop. The first launch may take 30 seconds. Yeah, we're not sure exactly why that is. We also happens to a couple people here, but not everyone. So don't worry about
Is
that.
your working?
It's a meme. So
It's working,
really
okay.
ignore it. Yeah, if the first image of the guy doesn't load for you, it's okay. We don't know why, but the important thing is that you actually get the GUI of napari, which might take 30 seconds.
This one.
If it's your first time.
I got the website link. I think it's some issue with GitHub. Copper. Yours, it's solved, right? Is it anyone else having issues? Issues? Oh, yeah. Let's maybe a minute, but it's just the first time because it's caching some things, and then it should be faster. But let me know if it doesn't work in a minute or so. But I think I can start with the introduction while it's installing or launching napari. How many of you know what is segmentation, image segmentation? Okay. Quite a few people, but not everyone, so I'll still give an introduction. But essentially, you want to group pixels, right? So here, there's like this example from Terminator where it has a vision that can detect and segment people. So you can see it delineated the boundary of the target. But a couple of examples that I think is very relevant for today is like autonomous vehicles. When you're like these vehicles that are being launched right now, they're trying to classify pixels if they're a person or a road or a tree. And there are two basic kinds of segmentation. So there's semantic segmentation when you want to assign a label to a pixel. For example, could be here I'm a person, and then you have the floor, you have the wall, and there is instance segmentation when you want to split different objects. And in this example, we will focus on the instance segmentation, which I think it can be thought as clustering, right? You're trying to cluster pixels into different groups. In this case, they're objects. And the semantic segmentation is you're trying to classify a class to the pixels. And every time you want to quantify something in the scientific environment, could be remote sensing, you want to count the number of houses, or in biology, you want to extract measurements from cells, you need to do segmentation because you want to get your imaging data and aggregate these pixels into your objects of interest. And in this context, the segmentation is well defined, but in the general context is a ill-defined problem, because if I just told you segment some images, you don't know which object you want to segment, right? You could say that I'm an object, or it could be my shirt could be an object, my glasses, right? So there is different levels of granularity that you could apply segmentation. So here, I'm going to start from the example from the scikit-image library, where we introduce segmentation. Okay, so we create 2 circles. This part, we are generating 2 images with overlapping circles. And then, wait, it's computing this. I hope it, oh, it didn't run, sorry. Here. Oh, here. Oh, one thing, if you open napari, you need to close napari to continue the tutorial. If you open with the exclamation mark. So this one example of the instance segmentation. We generated 2 circles, and we consider them to be our objects, and then we split them into different units. And we have this result where we have the background as 0 because they're not part of our region of interest. And then in the label mask, we assign different values to each instance. So if we evaluate the labels here, for example, if we do a NumPy unique on the labels, we should have 3 values. So 0 for background, this is kind of our standard, and then 1 and 2 for each object. Is that clear? And this could be seen as we have the background, which we want to ignore as 0, and then we have 2 clusters. I think this is the parallel analogy. Very often, segmentation, you need to have some feedback. Could be tuning the parameters and you're seeing the results you're getting, or you want to even do the segmentation interactively. So one tool that is very helpful to do that is napari, which is an image viewer that is, it has a bit more features than matplotlib. So here I'm instantiating the napari viewer, which launches, I think we can do this step by step. So here we instantiate the napari viewer. Let me make it smaller, just so you can follow it. Here. And what I'm going to do next is add an image, or input image, here. And then we can add additional layers. And this on the left side, these are the layers where you can interact with them. So I'm adding the labels layer. And you can see this call here added as an image, here added as a layer, labels. And they behave in different ways, right? The labels by default has some opacity. And you can visualize its contours. So you could visualize the segments by looking at the boundary of each label. And but you could have this label as an image if you want to. That's fine as well. Right. And you can change the color map, multiple things here. Okay, let's move on to the next one. And so if you're using the NumPy to generate some report or a Jupyter, it might be useful to use this function called notebook screenshot, where you can screenshot what is being shown in the viewer, and it will be shown as it was a matplotlib result. So I think the first exercise here is just to play around with napari. So there are a lot of features here for each layer. I think it could take 2 or 3 minutes to play around with that. I think it's always fun in napari to right-click everything, because there might be some features you're not aware of. For example, you have this image here. If you right-click, you can convert to labels or convert back to image. So let's play around for a minute. And if you have any question about napari or anything else, let me know. Okay. And is everything that I showed so far, did it make sense? Do you have any questions? Did you guys notice that you can paint on the labels layer? You can go back, you can add more layers if you want to. Here. It's painting and it's changing the data underneath it, and we can interact with it later. Was everyone able to change the opacity of the data, the visibility? Go to grid mode. So this is the grid mode. If you want to look at multiple images at once, here. And if you want to change the, let me turn this other one on. I'll go back to how it was. If you want to change the, how the grid is shown, you can change the width here, for example. And even in this, in here, you can paint this individual layer, right? If you want to fix how it was.
I think undo should work on that layer effect as well, like Control Z.
Yes, it works here. So if you do Control Z, you can undo the what we just painted. So we, is everyone okay here? Can we move on to the next part? Does anyone have any questions? All right. So just a sample data set. Now we'll load a different sample data set, but actually real data. So scikit-image provides some, oh, wait, it's not. So scikit-image provides some example data. Here we are loading the cells 3D data set from Allen Institute. And it comes with 4 dimensions. So the first dimension is the Z, which are the slices of the 2D plane. Then we have 2 different channels for different wavelengths the image was acquired. And then the y-x plane, as we are used to with 2D images. The data type is an integer, unsigned int 16, which is very common for microscopy data. They're saved as the photon count. So you don't have negative values or floats. So in this is the range of the data, the maximum value. Napari also enables using different scales for the axis, because what happens often, especially when you have 3D images, is that some of the dimensions might have different sizes. So here we are defining the spacing of the pixels, and then we are going to add the image in Napari. So image show here, it will open a new viewer, so you can close the viewer you had before. And by picking the channel axis here, it will split in different channels automatically, creating different layers. And because we provided the end display equals 3 parameter, the data is already in 3D. So you should be able to navigate it. And in this button, you can load, toggle between the 2D and 3D mode. You can change the perspective if you want. And everything you do in Napari in the main interface here, it can be reproduced through code. So if we go back to 2D here, and we rerun this, rerun the next chunk, we'll do a rotation according to the camera angles. It goes back to 3D, and it's taking a screenshot of the canvas. So considering in this case, we want to segment the cells, right? I think that's a very common application in biology. And we need to define a way to do that. So in this case, we could assume that the cells are split is where we have a high intensity of the green channel, right? And then we want to split this from the other regions, looking at the boundaries, so where there is a very large difference between color. So this is a scenario where the edge detection filters, which Lars just explained, could be very helpful, because where you have a big transition between colors, you have an edge after you pass the filter. So here I'm going to load each channel individually and normalize them. And we are importing the filters from the scikit-image package and running the far right filter, which is one of the varieties of edge detection filters, together with sharp filter and Sobel. But all these variants, they just try to make, they have extra assumptions about the smoothness of the derivatives. So let's run this filtering and include it in the image, in the napari. It's a bit harder to visualize in 3D, so we can go in 2D. But we can see here how it's highlighting the transition between what is the cell and what is the outside of the background. Is this clear to everyone? Where the gradient shows the edge detection, or the gradient shows the transition between colors? So the next step is to threshold what is the foreground. Because going back to what we mentioned, that segmentation is kind of like clustering. We can assume the edges is like the distance between the samples, the pixels, to do the clustering. And the threshold will show which samples, which pixels we want to consider, which ones we want to ignore. So we can apply a medium filter to denoise a little bit the images. And then from this, let's visualize the denoise image. We can add it in napari. The noise scale, let's see what's the spacing. And we can put color map equals magma. And you see here that when I added this new image, it blocked everything that's behind it. So you can change the blending, additive. So you can see what it's behind it, if you want to. And now that we have this moved image, we can try thresholding it. So we can go, I think the most widely used method for thresholding is Otsu, which essentially it computes you want to find a value where you can split the foreground and the background. What Otsu does, it computes the distribution of the it computes the distribution of the pixel intensities, and then it tries finding the threshold that will split the pixels into two groups, foreground and background, and get the maximum interclass variance. So you can see in this image here, as they're moving the value, which is the threshold, it starts printing the red line, which is the interclass variance. And in the middle, between the two distributions, you have the largest interclass variance, and then it computes the thresholding value automatically. Another variant here is the Lie minimum cross entropy threshold, which we'll be using. This one is a bit more complex, but it's, let's see, where is the, yeah. Okay, the formula is not there, but essentially it's trying to, rather than maximize the interclass variance, it's trying to minimize the entropy between the groups. So we have our denoise image. We can access the threshold function from scikit-image here. And we would threshold it and add this image to napari to evaluate the result. And we can see here is somewhat accurate, but we are able to detect ourselves, but we have some holes. So we could do some operations to try to fix these holes. When we are working with the images, mainly grayscale images or binary images, there's a framework called math morphology, where it thinks as these features of the image as kind of a topology or objects analyzing its shape. So some of the operations this framework has is to dilate or erode the object. And I think one operation that will be very helpful here is to remove small holes or small objects, where object is what is label 1 here. So we can import this submodule from scikit-image and remove we can pick a fixed width, take the power, the cubic power of this, because we are working in 3D, and we have a result with fewer holes. And here we do the same with the previous result, but removing small objects. And then we can add this new version in napari. So here we can compare the two results. So on the left side is after so this is the clean channel. Let me change to red here. Red is not green. Yellow. And the other one was before the morphological removal of small objects or small holes. Is everyone following? Everything clear? Okay. So now that we have a good foreground of our current result, we want to split the pixels into the different units, which will be our instances. We could start with the naive approach, where we consider each object to be a connected component. So if in the image space, so Let's convert these to labels. Let's visualize this here. We can, if you click here, you can shuffle the color of the labels here. So we have all the labels here. If they're not, if they're disconnected in 3D, we can consider them to be different labels. This is done by this label function. So I executed this chunk, and we have this new result here, where each object has its own label. But we can see this is not perfect, right? We had 3 cells that had the same label on the right side here, and they have they're touching, so they have the same label. And this happens as well in this other group of cells. So a better way to do that would be applying the watershed algorithm. And the watershed, it has 2 ways to execute it. You could use an algorithm to compute the markers, which are the source of the watershed, or you could do that manually. We start computing it automatically. And how it works is the how many of you are familiar with watershed? Okay, not a lot. So the idea of watershed is that if you need to imagine the image as a landscape. So let's go back to the edges. This is the ideal case for it. We go to 2D. So the image is a landscape, and you have lakes in each minima, as it was the valley of a topology. And the pixels that have higher values, they are brighter, right? And they are higher in this topology. So what you want is that for each valley, you'll be a region, and then you have the place where they meet, which is at the peak of the valley, the watershed. And that's why the algorithm is called watershed. So in this case, where it's darker, for example, inside the cell, should be a basin, a lake, and the background should be a different region. And then they'll meet in the boundary where you have a very clear separation between the objects, and this is the watershed, and this will result in different segmentations. So, but in practice, a lot of times we are providing these markers. So as if you had the topology of your image, so where the pixels that are brighter, they have higher topology. You make holes where the markers, and you're syncing that topology into a pool. And the regions that are being so the source of the watershed, these holes that we put for each marker, we will start flood filling your topology according to how much we sync, and this will delineate the segments. This started to become a bit abstract. Did it make sense to everyone? There's no whiteboard, but we could try drawing here. So let's assume let's hide this thing. Let's assume it's a 1D image. And we have something like this. So if we would assume that the watershed would run and you have a minimum here. You have three minimums, right? And so we have, this is our topology. We are sinking that in the water, and the water is flood filling here. So you have one object here, a different object here, and a different object on this side. So then we have 3 objects. Did it get clear? And so we can delete this. But the first step now to run the watershed is to compute the minimum, the source of the flood filling. And because our objects are convex, one way to do that, and let me show the labels again. One way to do that is computing the distance transform. We can visualize that as well. And let me also show the distance transform here. Here. So first, in this line, we included some points. They'll be easier to view in 3D. So you can see several points here. And interesting. Okay. And then you have the distance transform. The distance transform computed the distance between the border of the objects and towards the inside. So you can see here, if we inspect the values, so we can hover the mouse here. On the bottom left corner, you can see the values around here. You can see how here is around 2, and as we go further is 3 point something. So this is the distance of these pixels towards the border of the object. So when we are getting the maximum, we are showing these values. Let me invert this order and show the points here. So you can see here the points we just added, right? These are the maximum values of the object, of the distance transform. But this didn't work, right? We have much more points than we wanted. We wanted a single point per object. This is not the case. You see how many points we have here. But, now we could try finding not the actual maxima of the image. We could try improving by changing the parameters of the local maxima or changing the distance transform. Do you guys have any idea what could be done to have fewer maximums in the image? We can take a few minutes to think about this. This will be the first exercise of this step. I think as to showcase why this is not working, we could get these points and also run the segmentation from it. But for now, let's try improving the segmentation. Yeah, just to show an example, if we use, so here, what I did, I got the local maxima as we did before, right? And I converted to the different sources of the minimum of the watershed, because what the watershed function expects is different labels. So we can go here to the documentation. So the markers, did I run this correctly? Oh, wait, markers. Here. So I used I obtained the markers by relabeling the maximum. So let me include the markers as well. Add labels, markers. Scale. So here we can see we have each marker with a different color. And then I use this as input for the markers of the watershed. And the mask is the results, the binary mask we had after our operations. And this result is not great, right? We are over-segmenting our cells. So I think this is our first exercise. I'll leave this as a starting point, is how to obtain better segmentation. And we can take a minute or two to think about this. Does anyone have any questions? We can also discuss about different strategies to try to fix this. Is the local maxima clear to everyone? What it does? Yeah, I've seen some people that they're looking like a question mark to me. So what the local maxima does, it checks it checks the input for each pixel. It looks if there is a pixel with higher value around it. And for each connected component around this, it gets the maximum. So if we go back to the markers we have here, right? Where's the transformed image? Here. We have these 2 points marked as maximum, right? The yellow and the purple. So what happens here if we go to the transformed data? Here is 3.72. But if we look around it, all the values are smaller than this. So this is the maximum. But if we go, now we go to the, oh, it's not purple, it's brown. So we go to the brown, it's 3.95. It's higher than the other one. But the thing is, locally, this is the highest value. All the ones around it are higher, are smaller. So this is the local maxima. We can check what are the parameters of this function. So to change the number of the maxima and markers, we have two options, right? We could either change the parameters of the local maxima or change the input of the function, the transformed, this transformed array, which is the one we are visualizing here, the distance transform. We can take some minutes to play around with that and see. We could apply the filters that Lars showed us to see if changing the distance transform could yield different results. If anyone is stuck, we can also help. did anyone try to smooth the distance map or the peak local maxima functions suggested by the exercise? Okay, we can try going around this together. So because we are having we are having multiple maximums, one way we could try doing it is moving them out so they disappear and we might have a single one. So we could play around that. They showed a Gaussian filter here. Even though the data have different dimensions on z, y, x, they're a bit similar, so we can try using a single parameter here. Let's see how the results looks like. One second. So we could even evaluate what we had previously. And we can see for this one, this is not the maximum anymore, right? So we can try seeing how the results look like after this, just executing the rest of the function. So if with this one, we got very nice results. We are splitting almost all objects except this one, which is the one that is the most non-convex, right? And the thing why this is happening is because we are using the distance transform as input here. We could try using the image with the gradient that we computed before, the edges. Let me just check if what's the name of that image was.
That cell is dividing though, so maybe it should actually be treated as two objects. It's in the process of division.
That's true. We are all done here. So we could try running the edges on this case here. And does everyone know why I use the upside down transform here? The inverted, the negative value? Because before I was showing I drew the example where the center of the cell or the source is the valley, right? And the distance transform is the opposite. It has the highest value in the middle, so we want to invert that. So we just use the negative as input. We could even apply I didn't realize that we could use the smooth transform here. So we can rerun this using the smooth transform. Okay, it didn't change much, so it doesn't matter. But we can use the edges and see how it goes. And the results are better. It's almost perfectly correct, but then I think these two, they have the same label. Let's check the value here, 13. Oh, these two as well. So it's kind of I think this is very common in image processing, is the kind of a short blanket problem. You change the parameters, you fix one region, then the problem appears in a different region. It's like if you had a short blanket, you cover your arms, but then your feet is cold. Then you cover your feet, your arms are cold. So one option in this, what napari enables us, it can, you can add points manually to fix that. And then we could query that values back to an array and use that as input for the segmentation. So going back to 2D here, let's hide everything that we don't need. We can load the image. And we can, by running this cell, we add a new layer called interactive points here. And we can manually add the center of the region inside the cell, which will be the marker. So you go to this layer, you click at this point, and you can insert a point.
Maybe you want to make them a little bigger.
Yeah, they're too tiny. Let's see. You can remove them. 30, maybe? No, more. Did it get bigger?
Oh, I know what it is. You're limited by the OpenGL size. So you have a high resolution monitor, you're limited to 64. I believe pixels are all OpenGL can handle.
Oh, okay. Yeah, so yeah, let's 50 seems okay. And to resize all the points you had before, you can do Control A or Command A if you're on Mac and change the size of them. And then we can start fixing all the points here. Right. We could move them, and this will mark each cell we want to segment. Does anyone have any questions? Would you consider 2 cells here, Peter? It's hard to say.
Depends on what you're doing in the analysis. You may want to consider that different class, right? So you mark it with a different like color or whatever. If you're trying to get information about those nuclei, obviously that one is an outline. You would mark it as 2. I don't think it's hard to say.
Yeah, that makes sense. You can see the brightness here is very different. So you could skew your analysis if you're measuring the mean intensity, for example.
Yeah, if you wanted to calculate shape factors or intensity or anything, then obviously that's a pretty big outlier. You already see the condensed chromosome.
So let's put one marker here. Was everyone able to add the markers? Did anyone have trouble adding the markers? Okay. So now that we have the markers, we can extract the data back to as an array. So we just going back here, we created these points when we added the points, it returns the points layer here. And we can access the data by getting the points data. So we have the markers location, and there's this utility function from scikit-image to map the point backs to markers. And we can dilate these points. Let me split this up. We can take a look at the intermediate results. So here we can see we have an object for each cell. Hopefully I didn't miss any one of them except these ones that are cut in half. Okay. And then we can use these markers we just computed to run the watershed as we did before. So we have the edges, the markers, and the foreground mask. And then we obtain the result we want. But this image is looking a bit weird, right? This cell here. You can see the segmentation is a bit messed up. If we go back to the edges image, I think we'll probably find a weak boundary. So let's hide the labels here. You can see here there's a very weak boundary between the two regions. So this is where we are, if we think about the topology, there is no ridge, there is no watershed splitting the source of the water. So if we convert here to use the smooth transformed, which we created before by smoothing, or even the transformed, because this is a thing I added from in my own example. We could try running this one. The results could be a bit better. You see here? Hopefully it's better for all cells, not only this one. Oh wait, what happened? Oh, here. So we have a proper segmentation in getting the nuclei correctly. So usually you're doing segmentation with a given goal, right? You want to extract measurements to evaluate your experiment. So scikit-image provides some functionality to help you do that. This is the region props function. So here we are going to get only the objects that are we can remove the objects that are around the border because they could be outliers in our analysis. Let's see how it looks like. So we can see we have only the cells that are on the inside. And then now we compute the region props of these new labels we just computed. And you can provide an intensity image that will be a reference where it will extract some additional measurements. Because some measurements are based on the mask, the segmentation mask on the labels, so they don't require any additional input. But if you want to get the mean intensity, the standard deviation, these kind of things, you need to provide the intensity image. I don't know if is anyone work with biology here? No, okay. Because there's a very common package called Cell Profiler. The region props that they get here is very similar to the output of Cell Profiler. Yes, yes. I think the latest version is in Python, so they use scikit-image or something like that. So
They contributed a bunch of functionality to scikit-image as well.
to okay, then, I think that was I don't know the whole story, but it might be when they were implementing the Python version. Was it Alan? Right? Yeah. So here are some of the properties. We can extract from the object. And by running this, you can get a table where it can be loaded as a pandas data frame. For example, the area of each segment, the mean intensity, the solidity, which I'm not sure what it represents, but we can check out in the documentation. So okay, so we have a few extra exercises here. If you can, the area we computed, they're based on they don't take into account the physical dimensions, which we have in the spacing. How can we obtain that from the segmentation masks? And I think to do that, we need to use this new option in the region props, where you can pass custom functions here. So you could define a function here. The function by default, we can check if there is an example in the documentation. I think they take two inputs. Will be the label mask and the intensity image. So we can take a few minutes to look at, try to implement this where we compute the area in the actual physical dimension. Oh, they say here you only need pandas to do this. Okay. So do you guys want more time? Okay. So we can give it a try here. Check the area. Column, which is actually the volume of the 3D masks. So there's one thing I'm wondering is in this solution they suggest doing. I had to look at the solution to do the product of the spacing. But is that valid, or would you need to apply per axis and then multiply?
I mean, it's a multiplication, so it's supposed to be the same result, I think.
It's
Associated.
associated.
Doesn't matter what you multiply first.
Oh, you're multiplying everything together. Yes, that's true.
The product of the spacing gives you the
Mhm.
nanometers per voxel, right? So cubic nanometers for the voxel or whatever, micrometers, nanometers, whatever it is. And then you have the number
Yes,
of
yes,
voxels,
yeah.
so that you multiply one by the other.
Yeah, I was thinking about perimeter. I don't know why. Yes, yes. Sir. We can check here the results. And how can we visualize the last exercise? Is how to visualize this in the image if you want to propagate these values back to the object and be able to highlight or have a visual intuition what is happening. Does anyone want extra time? Okay, we can try doing this together. So we could call this image measurements, and we already import util, so we can map array here. Looking at the function it takes our input labels, interior labels, then the information from the data frame. So it's like we can get the area here. All right. Labels.
You coerce the NumPy, I think, to make it work.
But I don't think it's finding the value label. You can check here. Oh, it's the index. Right. So here we can visualize any attribute of the segments on the image space. Or we could change solidity here to see, try to see what is like. All right. Does anyone have any questions about any comments? So this was the segmentation part of the tutorial. We're almost at 5:30. I don't know if the other organizers of the tutorial have additional comments. But if you guys are getting into image analysis or image processing, computer vision, all of these packages we use, they have their own community chat. So if you go to napari community, you can reach out to everyone or even join the community meeting just to see what it's like. So here you can find the calendar. You are welcome to join any meetings, or you can join the chat and interact with the community. It's very active. I usually can't keep up with everything's going on, but you can find the different channels, and you can ask questions, make comments, whatever you feel like it. All right. Oh. That's ImageSC. Oh, that's a good one. So there's the ImageSC forum. Is a forum about scientific image what is this? Is science, right? Image processing for science, and then people discuss about software problems, bugs. They make announcement, job posting, this kind of stuff, and it's very active. You can see. And
You have the Slack, sorry. The inferior Zulu, aka Slack.
and this is not only for Python. So you see there are a lot of people use ImageJ, which is a Java software for image processing.
A lot of image processing tools in there. So if you have a very specific question to some image processing problem, that's probably the place to ask first.
Yeah, if you're using a specific library or tool, if you ask a question there, chances are the person who developed the tool or library
next flow. All right. Thank you, everyone, for the attention.
Since I'm here for the test, I'll have to connect to the project code just fine for my talk on Thursday. That's smart. Just want to make sure I don't need to like